Good afternoon, ladies and gentlemen. Welcome to the SAIEE Free State Centre webinar, where we will be discussing today the outline of renewable energies in South Africa. Before we start, just a few webinar considerations. Attendees are reminded to ensure the volume is turned up on their device. Ensure you have a stable internet connection. This will ensure the streaming of audio will run smoothly. Attendees can ask questions via the questions panel located within the GoToWebinar control panel. By default, the control panel is located on the right-hand side of your screen. The chat function is reserved for webinar organizers and panelists to communicate with attendees. Attendees will not be able to chat with each other, however, are encouraged to ask questions. A recording of the presentation will be made available on the SAIEE YouTube channel, SAIEE TV. The recording will also be made available on the SAIEE website under the Events drop-down menu in the section Past Events and Webinars. This page is updated regularly, so ensure you check back as often as possible for new uploads and subscribe to our YouTube channel. A certificate of attendance will be issued a few weeks after this webinar, once we have received the CPD validation number from EXA. I'd like to introduce you now to the chairman of the Free State Centre. It's Mr. Joseph George. Joseph is the chairperson of the SAIEE Free State Centre and is currently working as Senior Electrical Engineer in the Department of Public Works and Infrastructure in the Free State. Previously, he used to work for Eskom as a Field Service Engineer and a Network Planning Engineer. He has more than 10 years experience in electrical infrastructure planning, execution and design, and is currently specialising in renewable energy design. Over to you, Joseph.
Thank you, Minx. Welcome everyone to the second lecture of the series that we have here in Free State. I'm looking at the attendees now. Everyone, looks like a lot of Escomites are here. Thank you everyone for coming. We have two of our presenters here, Faure van Schalkwyk and Dr. Poole. As Ming said, we're trying to get this lecture CPD validated. So just wait a couple of weeks and we'll get that certified as soon as we can. So our first speaker is Faure van Schalkwyk. Minx, can you put on the next slide, please? Faure van Schalkwyk is an electrical and electronic engineer that obtained his BEng Electrical and Electronic and MH Management and Development at the Northwest University. He's currently providing training, consultancy, and advisory services in the solar PV environment to both the public and private sector. He manages a solar training center and is offering solar PV training and technical support for installers, engineers, as well as municipal and government officials that deal with distributed energy generation embedded on the network. He also formed part of the CSIR working group who compiled the SANS 10142/1/2. Over to you, Faure.
Okay, Joseph, thank you very much. Just want to move a few things around so that I can see everything. You just confirm if you can see my presentation?
Yep, we can see it.
Great, perfect. Okay, yeah, thank you, Joseph, for the opportunity. Minx for the arrangements, and thank you for everyone for attending today's session. My name is Faure van Schalkwyk, and I would like to briefly give an overview of renewable energy and focus specifically on solar PV. Dr. Sean will then come in to have a discussion regarding renewable energy in general. So there's a lot to say within 1 hour. So we will try to keep it interesting and concise as possible and make sure that you get the most value out of your hour. So let's, in terms of what I would like to discuss today is I will quickly look at what is defined as renewable energy. Renewable energy in South Africa, to have an overview of that. We need to, and then in the context of solar, we will look at solar resource, which is the substance that we will use to produce electricity or certain energy outputs. We will look at solar PV technologies, the efficiency and the typical energy payback period, the different types of solar PV systems. We'll look at the key two ones, and then energy storage options that we will typically see in South Africa. So what is if we talk about renewable energy, what is that, right? So from a RENEC source, it says the characteristics of renewable energy that often includes in the definitions are renewables are distinct from depleting fossil resources such as coal, oil, and gas. So if you look at resources that has a finite amount compared to an infinite amount of resources like sun and the wind and wave energy. Renewable sources of energy are thought to have an infinite supply. So there's like I said, you always have enough of that. The rate at which renewable energy is replenished is higher than it is consumed. If you think about, for example, using wood, which you can always plant trees again. And the renewables are associated with fewer environmental impacts. So it has reduced greenhouse gas emissions and therefore incurs lower external costs or damages as compared to fossil energy. And then all renewables are derived in one way or another from solar radiation, geothermal energy, and tidal energy. So you can see there's not a universal definition of what renewable energy is, but somewhere between these definitions, we have a common ground to understand where renewable energy would fit in. Now, if we look into renewable energies in South Africa, I'm sure as you drive around the country, you will see that there's various solar farms, wind farms, CSP, and other facilities built to generate renewable energy. And the chart which I got from Energy Block just indicates to you the different types of, let me just get my mouse, the different types of technology that's being installed all over the country. We've got CSP plants, which Sean will talk about, the concentrated solar power. And then we've got a lot of solar PV plants allocated in areas where we've got abundance of solar. And then we've got other forms of renewable energies as well. Now, what's giving us guidance in the South African context of what should be installed is the IRP, the Integrated Resource Plan, that stipulates and say, listen, based on all the energy generation mix that we've got, how much we will allocate for different technologies, including renewable energy, which is hydro, storage, pump storage, by the way, PV, wind, CSP. The yellow is the gray is indicated that's already being installed. The yellow is that it's committed or it's going to happen soon, and then the green is that's been allocated newly. And then something here on the side is then we call it small scale embedded generation or distributed generation. These are the systems installed on distribution level. So that's in municipalities, on your roof, on the business roof. So there's really an indication of planning to have a very big section of renewable energy. And just to give you an idea, we've already got about 10 gigawatts worth of renewables installed, and we're looking at additional 2,000 megawatts of renewables being installed in the next few years. If we look at pricing between solar, wind, and CSP, we'll see that there's a drastic reduction in cost of generation of electricity, especially for solar and wind. CSP is also a bit of a reduction, but that's also why you'll see that there's not much CSP allocation in the RRP going forward, purely because of the cost competitiveness that we are getting from other forms of technologies. Again, a resource I got from the CSIR, if we were just to compare the cost of energy, the levelized cost of energy, in other words, what is the cost of energy over its lifetime compared to other new build technologies, you will see that solar and wind is very competitive. We are already achieving a point where it's actually cheaper to install solar PV and wind comparing to operate coal-fired stations. So the competition is just increasing as we're going forward. So it already becomes a no-brainer going forward in terms of low energy cost. Now, talking about solar radiation, also something that Sean will talk about, we will see that in South Africa, we have a lot of energy that we can use. This is the solar source. In other words, how much kilowatt hours are we getting from the sun per square meter per year? So this is an energy amount. And we will see we've got higher amounts in the Northern Cape areas because we've got less cloud cover and compared to the coastal areas. And even if we compare our country to a country like Germany, you'll see that their highest values of 1,300 is still less than the 1,600 minimum that we've got in South Africa. So we have a lot of resources available in our country which we're not fully utilizing, whereas in countries like Germany, they've installed more than 40 gigawatts of solar PV. And they're not understanding why we're not using our opportunities or resources from our country. Now, if we want to convert it into, okay, how much energy can I produce? Then there's a chart that tells you that if you install about 1 kilowatt of PV on your roof with a performance ratio of 0.75, this is the amount of kilowatt hours per kilowatt peak that you can produce. So if you want to calculate, okay, I want to produce a certain amount of kilowatt hours or units per day or per month, or per year, then this is the chart to use to see what is the actual output after all the conversion, all the efficiency losses, what is the output that I will get from a typical solar system. And this is where this chart can be used for that. Now, if we look at solar PV production by region, we will see that we know that China is taking the lead on different solar PV production. We see that there's an increase of the rest of the world that's coming in. And I think after the COVID, we will see the rest of the world also increasing, because countries realize they need to become more independent and not be that dependent from China. Europe and US also took the lead at some stages, but you could see moving away to the Southeast Asian countries. If we look at the global cumulative PV installed over the years, you will see that there's a gradual increase going forward. And South Africa is only taking a small slice of the rest of the world, just showing you that the growth and opportunity for Africa and South Africa is still vastly, is very large. If we look at the three main types of technology that's being installed worldwide, it's thin film, mono, and multicrystalline. You'll see that multicrystalline did take the lead at some stage, but mono is gradually taking over compared to multicrystalline. This is due to reduction in cost and also the better performance and lower degradation you'll get with monocrystalline compared to multi. But we can see that there's a gradual growth, and thin film is also playing a smaller role worldwide. We look at efficiencies. We'll see that solar PV's efficiency has increased quite significantly in the past few years. The highest efficiency is already going beyond 20%, and this is just for commercial PV modules. You look in the laboratory conditions, you can even go up to 40% plus. I see the highest wattage rating here is about 500 watts. I already seen solar PV panels that's rated about 800 watts per panel. So we can see that the power output and the efficiency of these panels are increasing going forward. And we are seeing technology combinations where there's a possibility to achieve even a higher efficiency that we already see in the market. If we look at the energy payback time, so just to understand what this means, you need energy to produce the PV panel. You need energy to produce all the components needed for the solar system. And the question is, how long does it take before the energy produced from the solar system covers the energy that was needed initially? And if we look at the energy payback period between the different countries, even South Africa, we're looking at less than a year. In other words, if our solar PV system produces electricity for 1 year, it will pay back the energy required, not only to produce the modules, but all of the components. And that's great, because that's where you build or create more energy that was not there before. Okay, we know and are fully aware of various simple solar PV applications that can be used. We see this all over the country, even in your residential area or the countryside. And then we're starting to say, okay, how can we integrate this in even more in our society? So where it's used in products, where it's made part of tiles, we've seen these floating solar PV systems. So it's installed on top of the dam. It's forming part of structures, or even e-mobility. We spoke about solar roads. I think we saw solar roads as well. So there's various applications of how they try to integrate these technologies to fully harness the energy we could get from the sun. So here's just a basic PV system. There's no batteries involved. It's a grid-tied system, just so that we understand how this typically would work. So normally we would have a grid connection that we supply to a load or a house through a meter, and then we would install some form of grid-tied system. Now the grid-tied system would actually then synchronize with the AC, and then whatever solar is available from the PV side, it would convert from DC, change it to AC, and then inject it into the network. Your house will first utilize the power coming from the solar, and then the difference would come from the grid. If you are producing more power than what that you need, that excess power would then go back. Most of the solar systems installed in South Africa in the previous years was grid-tied, especially if you think about your macros or your shopping centers, because it made financially sense, and the payback periods for these systems were quite short. We're talking about anything from 3 to 6 years, and then it's paid off. As soon as you add batteries, then it becomes quite expensive, and the financial starts to become difficult to justify. Keep in mind, if the grid is off, then the system would not work. So it would switch off. So the main purpose for this system is to supplement your power supply and reduce your power bill. That's why you would install such a system like this. And just to show you practically how that would look like, the blue line is the typical load profile for a factory, and the green line is then the grid-tied system. So whatever is under the green line is then the energy offsetted by the solar system, which would reduce your bill from the municipal or Eskom side. So here's a hybrid or island system. I'm of the view that a lot of the systems that's being installed now would look something like this. where your PV is DC coupled. In other words, the solar injects its power on the battery side or the DC side of the system. And it gives you then the power supply that if Eskom goes down or there's load shedding, you still would be able to supply electricity from your battery system or from your solar system. You would then, in this context, use the utility to supplement your supply. So in general, we see a lot of systems like that. So it's not a case of people going off the grid, but they combine the grid supply with solar and some form of batteries for backup supply. And just to show you practically how the power energy usage would look like. So here you can see there's usage from the battery. So it's at nighttime. So we're using power from the batteries during the night, not much load. And then in the morning, the batteries was flat. So we would use the grid in that instance. As soon as there's sufficient solar supply, you would start to use the solar directly. That's the dark blue. And then excess solar would be used to charge the batteries. As soon as the batteries are fully charged and there's no loads to consume it, you'll see then this gray, that's power that's fed back to the grid. And then as soon as there's insufficient solar, you can then start using the battery power to supply your loads. And then you will continue through that process. So this is typically how the hybrid or the island systems would work. Okay, in energy storage options in Africa, there's mainly the following 4 things to consider when buying batteries. It's the cost, the life cycle, the maintenance that's required, and the efficiency. And I want to highlight efficiency because lithium ion compared to lead acid is much more efficient. So you can actually get away with a much smaller system compared to lead acid. So those are the 4 factors you need to consider when buying a battery. So the main technology used in South Africa is lead acid. We started off with lead acid. It's the proven technology that's been used all over the years. But in certain contexts, it becomes obsolete. So we need to consider other technologies like lithium ion. So this could be new or second life. Second life means that the batteries was used for maybe for EV overseas. It still has some good capacity to use in the solar sphere. And a lot of the second life batteries we will see coming into the market for a lower price that can be used for solar. Flow batteries or vanadium redox flow batteries is another form of storage. But it really makes financial sense or utility scale to apply or use that. And then we know about supercapacitors. So supercapacitors is also a new technology on the table. There are various views on it. On paper, it seems very good because it has an enhanced lifetime expectancy. But the guys that's in the field says that if you look to it closer, it's actually a combination of supercapacitors and a very advanced lithium ion combination. So, so it is a good option to consider, but it's still a new technology that needs to prove it going forward. Okay, so that is in a nutshell what I want to talk about on the solar side. I just also want to highlight that if you are interested in the solar PV sphere in terms of designing, installing, commissioning solar PV, we also provide specifically PV green card training that's accredited by SAIEE. We also aligned with the AREPS P4 or P4 level 1 test. So we actually provide preparation for that. And if you are interested in the training itself or would like to become a PV green card installer or certified installer, feel free to contact us. There will be a survey, by the way, at the end of the training where you can provide your contact details and we can provide you more information about the training, the benefits, the cost, the venue, and so on. Okay, Joseph, thank you. That's all from my side.
Great, thanks, Faure. It's actually interesting that you said that because just yesterday I was on the Canadian Solar website and I saw that they just released a PV that's 665 watts, which is like double your normal wattage of a solar panel.
Yes, that's right.
So you're right, yeah. It's getting more efficient, much more efficient.
Yes, yes, and it's typically with the half cell technology that they increase the wattage output, and that's why you're starting to see panels that's going up to 800 watts per panel, and that's amazing to see.
Oh, that's good. If anyone has any questions, you can either raise your hand, then I can unmute you, or you can put into the chat box. Then I will read out to Faure or Dr. Sean Poole, whatever questions that you have. Yes, Sean? Oh, raise your hands like that. Our next presenter is Dr. Sean Poole.
I wanted to ask, what are the size of those panels? The 800 watt panels, are they a similar size or are they growing at the same time?
So in the market, you would typically have a 60 or 72 cell panel. Your 60 cell is normally a 1 by 1.7 meters. your 72 cell panels are 2 meters by a meter. The 800 watt panels, I'm going to be honest, I'm not 100% sure. I would say it's similar to the 72 cell panel size, which is about a 2 meter by 1 meter, or 2.1 by 1 by 1, which is very similar to your 72 cell panel size. So the support for that type of panel needs to be quite proper, you know, in terms of the mounting that you're going to install. But if there's anyone that could correct me on the size, I think that's more or less the size.
Okay. Okay, thank you, Faure. Our next speaker is Dr. Poole. Sean has a PhD in mechanical engineering, focusing on small wind turbine blade design. Sean manages various energy-related projects and lectures and renewable energy short courses at the Nelson Mandela University in PE. He has been involved with renewable energy research at NMMU since 2013. Another interest of his is prototyping and concept design, which has led to the founding of his company, ProVolution. Over to you, Sean.
Great, thanks. Okay, so I'm going to also do lecturing for AEPA. They've got a renewable energy professional, this REP course, so I've drawn a lot of the material from there. It's usually a 3-day course, so we're trying to pack 3 days into 30 minutes. So I've pulled out a whole lot of slides and pictures, which are hopefully going to keep your attention. And I've tried to keep it as simple as possible, but at the same time, just make you aware of possibilities of where you could apply these different technologies within South Africa. Okay, so what we're going to present, the why and the what, kind of briefly.
Sean, is it possible you could just move the presentation to the center of the screen? I don't know if it's only me that's seeing it on the side.
Oh, is it? Are you seeing my whole screen?
Yes. Joseph, you can also just maybe confirm.
Yeah, I'm only seeing half the presentation.
Now, could you make it a little bit smaller?
The presentation smaller.
Yeah, to put in the middle.
Oh, I see. Sorry, I see there. I don't know why. Okay, I'm trying to make it fit to that.
Yes, that could work.
Okay, is it fitting in there now?
Thank you. Thank you, Sean.
Okay. Okay, sorry about that. Okay, so the what and the why, kind of similar to what Faure has covered already. We'll touch on solar thermal, geothermal, hydro, wind energy, and then biomass. And then I'm hoping guys will have some questions on these various topics. Okay, so firstly, what is sustainability? And I just copy and pasted this definition there from Wikipedia. Sustainability is the ability to exist constantly. So in the 21st century, it refers to generally the capacity for the biosphere and human civilization to coexist. So whatever we're doing, we need to make sure that this relationship with the biosphere is going to last indefinitely. And if we continue to burn fossil fuels as the way we are doing it now, we are not going to be in a sustainable biosphere, and things are going to turn for the worst. So that is the reason why we look to renewable energies, because they do not emit any, in a lot of cases, or very little CO2 into the atmosphere. And so it is a much more sustainable solution. And so that is the driving force, at least originally, behind renewable energies. As you saw, the cost of renewables is now switching to actually make it more financially viable compared to fossil fuels, which is great, because now we don't have to justify it. It should happen naturally. So what are renewable energy technologies? So we see here, we have different types of energy. We see the sun there, we see the wind on the right, and we see the waterfall. And then we have some sort of technology that will harness those forms of energy and convert them into the form that we require. So most of the time it is electricity. Sometimes it's heat, sometimes we have cooling, but the most common is electricity and then heat. And so this renewable energy technology is just a conversion system. How are we going to take wind energy and make it into electricity, and what's the best solution? And yeah, that's technically what all these technologies do. And we saw this slide already from Faure. We can see the large scale plants around South Africa. This is specifically through the REI4P program, which is a government led program to connect utility scale renewable energy to the grid. Okay, on to solar thermal there. We see a very similar resource map compared to what Faure was showing. The main difference here is this refers to your direct normal irradiation. And when you are dealing with solar thermal, a lot of the time you need direct rays, and you'll see in the pictures coming up that you can reflect onto a specific point. And if you don't have direct rays, you don't have any energy to work with. So if there's a slight mist or a bit of cloud cover or haze, and you lose that direct light, you don't actually have any rays to work with. And so you're measuring the sun's energy in a slightly different way. And so when you are dealing with solar thermal, you are looking at direct normal irradiation. If you are dealing with PV, you're normally looking at global horizontal irradiation. So there can be slight differences between maps that look fairly similar, and that may be a reason as to why they are different. So here's a couple of pictures, and I can't seem to get my marker up, doesn't matter. On the top left there, we see a power tower system. So all of those little mirrors, so they're not so little, it's probably about 4 meters by 4 meters. They are individually controlled, and they reflect the sun's light onto the top of that tower, and that heat then is used to generate electricity. Much the same as a coal-fired power station would use coal to heat steam and run a steam turbine. This simply uses the sun's rays to heat the steam either directly or indirectly, and then run a steam turbine. So the business end of these power plants is much the same as a coal-fired power station. On the bottom right there, we see a parabolic trough where you have this shaped mirror reflecting the light onto a tube, which is then collecting the heat and transferring it to some sort of transfer fluid. Interesting thing here with this type of technology is energy storage, and we see that in that massive tank on the bottom left, and there's 2 tanks there on the top right picture. And what they do is they store the heat that's collected from the sun in those tanks like a giant flask, and later in the day that can then be used to produce electricity. So you could decide not to produce any electricity throughout the day and then run your power plant through the night, which is quite unique compared to something like PV, which the storage is quite expensive. Storage on these systems is obviously an added cost, but it's an advantageous and easy way to extend your power output. We have plants that are producing energy 24/7 like this. So they may run at 50% capacity 24/7. And you have sort of, you could call it base load output. Other solar thermal technologies, we see on the left there these collector tubes on a low pressure system. And I think these are, everyone's familiar with these. We see them throughout South Africa. There was a government program where they installed, I think, 2 million of them across the country. So fairly simple. Again, you're just collecting the sun's heat energy directly and transferring that to the water, which you can then use later. On the right there, we see some flat plate collectors, which are doing very much the same thing. They are collecting the sun's energy and transferring it to the water. Another option for hot water heating may be to go PV direct, and I have this at my home here. You use the energy coming from the PV panels, and then you dump that into an element in your geyser, and you create your hot water like that. Another option, and a fairly simple option, which could be installed on most buildings, is something like this trombo wall, and it's essentially a gap on the outside of your building where the sun rays can come through the outer surface, so a sheet of glass, and there's a greenhouse effect there. The heat is trapped in that wall, and if you have vents at the top of the wall, that air then rises and then vents into your building space. So a very simple way to create space heating, and fairly cost-effective way. And I mean, I don't think I've ever seen this in South Africa as an example on a building, but I've seen many pictures of overseas. So this is definitely, I think, something we could utilize more in South Africa. And then here we see solar thermal cooking, which is again a very simple concept. We're just redirecting the sun's energy onto a point, and we put a pot of food there. At the university, we've made a couple of these, and every now and then we would have a braai on a Friday afternoon where we would just put some boerewors in a pot, stick the thing in the sun, line it up to get all the rays reflecting, and then you've got roughly a kilowatts worth of energy, which is equivalent to your stove. So for every 1 square meter of sunlight, that's roughly 1 kilowatts of energy. So here we see 1 square meter solar cooker equating to a 1 kilowatt cooker. Yeah, well, one kilowatts worth of energy. Here are some examples. This is Bokpoort in the Northern Cape, and you can see that on that map. If you go to energy.org.za, each of those little dots, you can then click on it, and you can see some information about that plant. So these are typically around 50 megawatts, the solar thermal plants, producing electricity and feeding it into the grid. This specific one, Bokpoort, has the ability with its storage capacity to run to produce energy 24/7. Okay, on to geothermal. So again, the resource, the direct or the most obvious geothermal resource is some sort of lava or heat from underground, but there are many other geothermal resources that can be used, and we will go into that during this. So firstly, that heat underground, we can use that heat underground to heat up water. We can then pump that water or extract it out of the ground, and we can convert it or transfer that heat to steam, or sometimes we can even use the steam directly from the ground. But in the end, we run a steam turbine, much as in a coal-fired power station, and we produce electricity that way. The great thing about this type of renewable energy resource is that we're producing electricity 24/7, because when the sun goes down or the weather changes, you're not really changing, or you're not changing at all the temperature underground, and so you can constantly extract heat from underground. If you look at that picture there, point number 5 refers to an injection well, which is very important with these type of systems. You need to make sure that you replenish the water back underground, because you may come to a point where your power station has been running for 10, 20 years, and then suddenly there's no water underground anymore, and now your power station is essentially useless because you can't extract that heat from underground because there's no more water underground. And so you need to manage that water resource carefully. Sorry, going back there, South Africa, we don't have this type of resource. Mainly in Africa, it would be Kenya. In California, they've got a lot of this. Iceland, they've got a lot of this. So not really applicable to South Africa, but I just put it in here to show that you can produce electricity from geothermal. Here's something which applies very well to South Africa, using a ground source heat pump. So generally when we have an aircon in our office, what that aircon is trying to do is trying to get rid of heat on the outside of the building and absorb heat from the inside of the building and therefore cool the building down. And if the outside is hot, it's very difficult to dump heat into a hot environment. So an easier way of doing that is you run your piping or your cooling pipes underground, which makes it much easier to dump that heat from your air conditioner or your heat pump into the ground, and therefore increasing the effectiveness of your air conditioning system. The reverse is also true. Using a heat pump, you could also absorb heat from underground. So if you were in a very cold place where it was snowing, you could use a heat pump, and instead of trying to absorb heat from a cold, snowy environment, you would then be absorbing heat from underground. So this is a great application. I've seen this at the Verda Hotel in Cape Town at the airport there. They've got kilometers worth of pipe underground, and they use this for their heat pump systems, which heats water and cools water. And I'm not exactly sure what they do with it. I think it's for the air conditioning, stuff like that. Another example here is using earth cooling, which is again very simple, but I've never seen this done as a practical example. You essentially have an inlet pipe which pulls air into your building, and you would know on a hot day you dig a hole a couple foot under the ground, and generally the soil is quite cool. And so you're using that to your advantage. So you run piping underneath the soil, maybe a meter down, and before that air manages to get into your building, it is cooled down by the mass of soil, and you have cool air getting pulled into your building. So either you could use this directly just with a computer fan, and you're drawing cool air into your building, or you can run that into an aircon unit, which would then cool it even further. So very simple, can be very cost effective, and your energy requirement can be just, tens of watts running a small fan. Okay, on to hydro. So there's a little bit of the hydrologic cycle where the water is evaporated off the ocean, and it is condensed into clouds. That then generate precipitation happens at a high elevation. And now we have water that's at a high elevation, which we can then use to our advantage. That potential energy, we can use that to run devices to produce mechanical energy or also produce electricity. So an example there of how simple it can be. There we see a Pelton wheel in the center of those pipes there. Very efficient, a Pelton wheel in your 90% efficiencies. Very simple. You can, me being in the 3D printing game, you could 3D print something like this. And if you were very lucky to have a farm or something that you have a stream running through your farm with a little bit of an elevation drop, you could get 24/7 power from that stream. So I would say, in my opinion, this is kind of the holy grail of renewable energy. But obviously not very common compared to something like solar PV, where everyone is going to have sun shining onto their house. This is the other end of the scale. We see a dam wall there, Three Gorges Dam in China. You may have seen this in the news lately. A lot of pressure being put onto this dam wall because of the flooding happening in China. But this is a 22.5 gigawatt power station, and so they could, you know, power the majority of South Africa just off this one power station. So it's massive. It's the biggest in the world, but that is the other end of the scale, and also very cost effective. So we do see this in South Africa, not to this scale, but we do have a couple of hydropower plants, and we also use it for storage, where we pump the water into the dam when we have excess power, and we draw on that power through the turbines when we need it. Just a quick calculation there. So your two key things there being your flow rate and your height. So if you're considering installing hydro, you know, at a site, you need to know you've got to have a big head or height drop, and you need to have a high flow rate to get a good amount of power coming out. On to wind energy, again focusing as always on the resource first. You can see South Africa has very good wind resources across the country. Yeah, there was a study done by the CSIR where they consider putting low wind speed wind turbines in low wind speed locations and high wind speed in high wind speed locations, and the amount of potential across the country is just vast. So it is really an untapped resource, and we are very privileged to have both really good solar resources and really good wind resources in South Africa. And so technically we could have the cheapest electricity in the world because renewables are becoming the cheapest technology to run, and we have the best resources. So we would get the most out of those technologies. Just a couple of key data there. So there's a plan for 6 gigawatts of wind by 2030. We're now supplying 52% of South Africa's renewable energy power. This is the wind, you know, compared to your PV and your concentrated solar power. What other third last point there? 22 operational wind farms. They are generally limited to 140 megawatts in size. Just over 2 gigawatts connected to the grid already, and 900 turbines spread out across the country. We see the wind tariffs have dropped by 59%, as you saw in that slide earlier. Not dropping as quick as PV. PV has dropped substantially and is now maybe even cheaper than wind, or matching wind, where wind used to be the obvious technology when it comes to cost effectiveness. It seems like the CSR has popular data to take. So I've also taken a bit from the CSR. They did a little study in 2015. They took 1 month in January, and they logged all the data coming from these utility scale PV plants, and they also logged all the data coming from the wind plants. So you'll see on the, I don't know if you can see my pointer, but anyway, on the left-hand side, you can see a clear peak in the center of the day, which is obvious to wind energy, to solar PV. The sun shines during the day. You know you're not going to get any power at night. But an interesting thing is, on the worst day in the summer month, solar produced still at 50% capacity. So it is still a very reliable source. And as the capacity increases across the country, so that reliability will increase at the same time. Similarly for wind, we have a good aggregate, and the more wind that's installed across the country, the more we can rely on wind, simply because the chances of it not blowing in Cape Town and in Port Elizabeth and in the Northern Cape and in Joburg, you know, wherever we have these turbines all at the same time is really minimal. and so you should be always getting power from somewhere 24/7, if not at at some partial capacity. But a very interesting thing that was shown here is at roughly 6 o'clock in the evening, which matches our peak Eskom's peak supply time, wind seems to increase in power. So in the afternoon, we have this nice spike in wind power, and it matches the spike in demand, which is a great characteristic of wind energy. Yeah. Oh. Okay, so there's some technologies, just highlighting the difference again in the wind energy sector. We've got that small wind turbine at the top, a Kestrel, produced locally in South Africa, in Port Elizabeth, maybe a 1 kilowatt. And then the picture at the bottom there, maybe something like a 3 megawatt wind turbine, also producing power. So you can see very much the same concept, but on two totally different scales. And wind scales very well. The larger you make your turbine, the more cost effective it becomes. And that's largely due to your swept area. Your swept area increases to the power of 2 as you increase your blade length. But also the higher up you go, the more the wind increases. And so there's this twofold factor as to why the larger wind turbines are more cost effective. And so we see this clear trend of turbines getting larger and larger and larger. Here's an example of some wind turbines in South Africa. Here I have Van Staden's 3 megawatt wind turbines. And here just down the road as well, Jeffreys Bay, there's 60 2.3 megawatt Siemens wind turbines. These are some of our early plants. And then the last section is biomass, and probably one of the most diverse and maybe complex systems. We see in the top left there some algae being grown in the sun, which is showing to be a very promising form of bioenergy. On the top right, we see corn, which is used to produce ethanol. On the bottom left, we have wood, which is obviously a very common form of bioenergy. When we burn the wood, we produce a lot of heat. And then the bottom right, we can see sewage there, which we can use to produce methane as it decomposes. So the renewable cycle there is a little bit more complex. And the question is, we're burning wood, for example, and we're emitting CO2 into the atmosphere. How does this make it sustainable? And it makes it sustainable if we are planting those trees to reabsorb that CO2 we've just emitted into the atmosphere. And so we sequester that CO2, we store it back into the trees. And so this closed loop cycle should hopefully have a zero net effect on the atmosphere in terms of CO2 emissions. Generally, with the transport, for example, we're not burning a biofuel, we're burning petrol or diesel, and so we are emitting slightly more CO2 into the atmosphere than what we are absorbing. But ideally, you want a net zero system. Here are some examples on the left there, just again highlighting the vast range in technologies. The left is a biodigester, which you could install at your house. You throw in there waste food, sewage, any biomatter, and that would decompose and produce methane. You can then use that methane to cook off as an energy source, and also break down those waste products into a fertilizer. In the center there, we see a very efficient cooker. You see a little pot on that stove, and yeah, so probably pellets or some wood is loaded into that system, and you can cook very effectively on a small amount of fuel. In the top right there, some sort of electricity production most likely biodigester, a large-scale biodigester producing methane, which will be running some engine, which will then be producing electricity. And then bottom right, very simple form, just using that stored energy in the wood to produce heat. And that is my 2 cents. I think we can then have a look at any questions. If you've got any questions, please launch them in the chat there. Yeah, if you are keen on learning more about all the different technologies, you're welcome to attend one of our REP courses. Yeah, thanks for listening. Joseph, back to you.
Thank you, Sean. We have a couple of questions here. From Hafiji says, the RE comparisons don't include hydro. Is there a resource that does include hydro to show the LCOE comparisons?
I think that's a question to me.
I think so.
Yeah, I'm not sure about the slide, but I'm sure that it can be included. But I think one thing that we just need to keep in mind is that there's a difference between comparing the operation costs and the new build costs. Unfortunately, in the past there was reports where they compared operation costs to new builds. So when you see the LCOE costs for solar wind, for example, it includes the capital expenditure cost as well. So if we want to compare it with hydro, it's important to include the capex cost as well, so that you can really see the comparison, because we know that the operation cost would be quite low if it's almost nothing, you know, for hydro. But yeah, I'm not sure why it's not included or shown, but we do plan to do install or realize some hydro as well, as it can supply some base load.
Okay. Hafiji also mentions that you didn't mention standalone systems, which are off-grid systems. What are the advantages and disadvantages of that?
Sure. Okay. I haven't covered it, but you are right. Standalone system or off-grid systems is also very common, especially for rural areas where there's no ESCOM connection. So if there's no municipal or ESCOM connection, it could be much more financially feasible to rather build and install an off-grid system if you compare it to the cost to get a new connection from the utility. It's, like I said, something that I will typically advise on if it's quite remote. There are the question, you know, the typical question people would get is it possible to go off grid if you are already supplied by municipality or ESCOM? The answer is yes. But if you're asking me if it makes financially sense, then I would say sometimes, not always. It's most of the cases it won't make financially sense. There are cases, for example, if you have an ESCOM connection and your fixed network charge is more than your energy consumption. These are cases where it could make financially sense to totally go off grid. But in municipal areas, we don't necessarily have that fixed charge, or your energy consumption is, you know, much more than your connection. Then it could be that it would maybe still make sense to keep that connection there and then complement it with a hybrid or island system. So yeah, so standalone off-grid systems would mainly be for remote sites, and in some cases where it makes financially sense, and also to consider pure DC systems. In other words, your solar PV, your charger, your battery, your loads, everything is DC operated. It means that you've got much less losses due to conversion efficiencies, and you can actually realize a smaller system compared to a system that requires some inverters. But that's like very specialized applications if you want to have a pure DC system.
I think also the part that people forget the most is that for the off-grid systems, you need batteries, and batteries need maintenance, and those have to be done yearly, and those aren't cheap if one fails.
Yes, correct. The thing about hybrid systems or off-grid systems, and that's typically where the financial part becomes tricky, is the cost of the battery that you need to add. Now, you would argue that yes, there's maintenance for lead-acid batteries, but there's no maintenance for lithium. Even if you have to check the voltage values to make sure that it's correctly charged and that it's balanced, that is a form of maintenance. So all batteries would need some form of maintenance to make sure it gives you the lifetime of the cycles that you would expect it from. But yeah, it's mainly the cost that's a big issue. I mean, any solar system with batteries, easily the half of the cost would go to batteries alone. So yeah, it is a big cost component.
Ben
So
Coates also asked,
me, for example,
sorry,
Joseph.
go ahead. No, go ahead.
Sorry,
Please.
so I do 3D printing, and my printers sometimes, run for days on a print, and so I can't rely on Eskom. So for me, the cost of batteries is such an easy decision because the alternative is to rely on Eskom. So I'm not even looking at an energy point of view. I'm looking at what my reliance on energy. So that might be a question. You could say, if I'm losing 2 hours of production each day, what's the value of that? And it could be quite a lot, and it could easily pay off batteries. So that's another question you may have to ask.
Yes. No, Sean, you're totally correct. I agree. And that's always the challenge, is how do you quantify the benefit of having power when there's load shedding? What is the production loss that you would have if you had load shedding? If you can quantify that and it justify the cost, I mean, then it's a no-brainer. The unfortunate thing is people think that will apply for residential as well, because how do you quantify the benefit for that, just for having power in the house? But for business operation, I totally agree. There are cases where you would look at it from a reliability point of view and not an energy savings point of view.
Okay, thank you. Ben Coates also asked here, have you done some hybrid or e-vehicle charge stations?
I'm not sure about the hybrid stations. I'm personally not involved with any EV stations that's being installed, but I am aware that there are some programs where they're putting out some EV charging stations. But I haven't been involved with any of those. Sean?
Yeah, so at the university here, we've got a center called Uyelo, and they have mandates to assist on a national level with the rolling out of electric vehicle infrastructure, etc. So they have they've done some testing. They've reused vehicle battery systems with a solar system to charge vehicles there. So they've managed to charge the vehicles at the charging stations there. It would either be directly from the PV or from grid or from the battery, and even when you may need it, Eskom may need, or the municipality may need extra power, you can then use that system to feed back into the grid and supply power through the batteries or through the PV. So they're playing with that. Obviously, that's kind of like the end goal. If everyone has a electric vehicle in your garage and you plug it in, you've suddenly got a huge amount of energy storage available that the utility can tap off, and then also you have a small little business case there. When they use your power, you're charging for it, so you can actually make money off your vehicle.
Yes, and if I can add to that, it could also then serve as an alternative to having storage in the house. So instead of paying a lot of money for a big storage system in your house, you rather use that money to spend it on an EV, and you can then use the EV for storage for your house operation. So in those cases, you can cut out that double cost.
I just wanted to tell Sean that there's a documentary on Netflix called Down to Earth. It's almost like they explore sustainable solutions, and in the first episode they actually go to Iceland and they explore the geothermal. Yeah, and it's actually quite interesting that they actually go inside the plants and they show the machinery and everything involved. It's quite interesting.
Musical guy.
Yeah, I don't know, the one that my wife likes so much. I don't know.
Yeah,
okay.
It was very interesting. So they were also producing like minerals and some weird stuff from what they were drawing from underground. So it's very interesting.
Yeah, and it's actually interesting, like the whole culture is now revolved around this geothermal, and a lot of the spas and all the energy from there. I just wanted to just give feedback. Faure did say that he did some research on the 800-watt modules, and he said that the size of them is 2.5 meters times 1.76 times or 2.36 times 1.6 with a quadruple layer of 47 half cells. And the standard 400 watt modules has 72 and it's 2.1 times 1.1. So basically it's the same size, but now just double the power.
Yeah.
It's amazing.
Thank you for that, Joseph. Maybe I could pose a question to Joseph if there's no other questions. I think it could be interesting for the audience as well. So there's some of the renewable energy technology that can provide some form of base load. We heard that geothermal can do that. We know that CSP that can store the thermal energy can do that. A pump storage will also be able to do that. But in terms of being able to fluctuate or ramp up or down, not all technologies can easily do that. And I was under the impression that hydro could easily do that, but it seems like for most hydro technologies that's not the case. Even for water pump schemes, that you need to get a fixed output from them, and you cannot ramp it up or down. Is that true, or is there other technologies that's addressing that?
If anyone from the audience, from the attendees can answer that?
Yeah, well, it's actually a question for Sean as well, yeah.
If you want to talk, raise your hand and I can unmute you.
It's a matter of minutes, or maybe half an hour at most for something like Palmit, which is a pump storage station, because they use that as a peaking station. So, it's not days or hours as other technologies. But I like what you're saying, and also the fact that a lot of the renewables, if you take solar PV, for example, we're talking about milliseconds for it to adjust to requirements. So if Eskom are suddenly wanting 50% power from a plant, they can do that, with a click of a button, which other technologies don't offer. And we're seeing these PV and wind farms, they are also contributing to the stability of the grid in terms of controlling their power factor, controlling the voltage, and also they now do fault ride through. So if there are glitches on the grid, they try and kind of stabilize the grid before they shut down. And so there are actually benefits to the grid by having all these renewable energies connected.
Yes, I agree, and I would like to add that in the 2015 load shedding that we had, if it was not for the renewables, we would have much more or much higher levels of load shedding, and the savings on diesel generation would have it was also quite substantial due to renewables that was in place. So yes, you are right. It does play a role, not just in terms of energy production, but also to stabilize the grid in general, if it is done properly.
Okay, thank you. Does anyone have any more questions? Okay. The presentation and the webinar will be loaded onto the SAIEE TV website. You just have to go to SAIEE and then look for SAIEE TV, and all the presentations will be there. What else? Am I missing anything else? Nope, don't think so. Yeah, thank you everyone for participating. We really appreciate you guys joining us for this 1 hour. At the end of this webinar, as soon as you log out, you'll see there's a survey. If you have any more questions or you have something to ask presenters, then you can just complete the survey and then they will get it. So if you have any more further communication, you can either put into the survey or you can email me, and I'll make sure Faure or Sean will get back to you. Thank you everyone for participating, and I'll hand it back to Minx. But also thank you Faure and thank you Sean for coming and talking to us today. We really appreciate you guys taking the time out and come and talk to us about renewable energy. We really appreciate it. Thank you guys.
Thank you. Thank you.
Thanks.
Minx, can we hand it back to you?